We're on.
Amanda, are you there?
Yes, I'm printing off test corrections.
Okay, thank you. That's what I was going to ask if you got them yet.
I have a question about Isothermal page. So I can see my final grade, but I can't see the individual grades. Is there a reason you can't see? Well, how do I know? What if it's... You actually really look the same. Really? Yeah, like your face looks very similar. You were so cute.
It's just a smaller version of myself.
That's so cute. All you need is
College counsel's next week. ISA level 2 for next spring, and I will also be.
Alright, you might as well come up and get your...
And they think this, that's, these people make correctly. I'm doing that for the people that I'm trying to not break. And so that's getting all the time. Okay. So, I really don't like any section against me.
What's your stupid name on it?
No, because both of my papers had names on it, and I only had...
So was my grade wrong then? Or...
Yeah.
I would say it's great, but she's been on
Let me
the
give
job.
you your originals too, and there's a stick personal stick on.
Only my
Unfortunately, what if things happen, you know?
Well,
What if the
that-
things
that-
happen?
I'll write your name on all of them.
I still need... So,
Yeah.
I guess it isn't that hard to tell mine apart, because I still wish...
Susie, you have your original.
They're not hard to tell apart.
So at least which page am I missing?
What you mean?
I'm a happy boy.
Does it look like
Okay, okay, Mason.
Mine are easier to tell apart because they're yellowish.
Your question, right? Or you
Yeah,
question
square.
wrong, but then you read the
How did I get it wrong? What was
I
the...
Thanks.
Wait. I got
4D.
one wrong. Thanks.
4D. I got that.
Okay, Brittany, come around here. Which one?
What's the other answer?
Did you get this
Sorry,
one?
you're sick.
That's the page you need.
And I need the
I almost got a 100. Dang it.
Okay.
But, yeah, I'm pretty happy. I'm not complaining.
You got something?
I'll take whatever I can get. So I realized something. You sleep at 3:30. So you have to wake up at 6 o'clock. You're getting like 2.5 hours of sleep.
The meeting's fine.
Are you still getting a haircut today?
Yeah. Can you drive today? Kind of don't feel like driving today.
That's the same.
Please. Thanks.
But
You know what?
Final percentage or
I'll take it.
points added to the fraction.
We'll take
the
it.
rack.
No, did you?
All right, I think everyone has their corrections now.
Should I ask?
Number 4.
Positive.
I'm not.
Ms. Klinger, our extra credit points, are they added to the percentage or to the fraction?
I can't believe it.
Ask him.
The D's not zero.
So, Mr. Gadd.
Damn.
We have a question about the extra credit points.
Yes?
Do the points we got for extra credit, is that added to the percentage or to the fraction grade?
It's definitely not a percentage. It is points, and it's just points you put into the total pot of points that you earned. So, 20 points that we had so far with a previous test and attendance grade and homework and stuff, and now you have that many more points added into your total pot. Effectively, if you would like, you can visualize it as being added onto your test grade. Honestly, in the grade book, I don't change your test grade. I simply make another value that says here's the extra credit you earned. So I still know your original test grade, and I know how much extra credit.
I'll take it. I'll take whatever I can get.
So take what you got.
Yeah, I'll take whatever I can get. I'm a scavenger.
Let's talk about this for just a moment. There were apparently a little bit of misunderstanding on this first time out on what's expected and what you should do. Rules are that each problem that you don't get all the points you need to redo. Notice on your test, each problem number has some points assigned to it, and then has some subparts, part A, part B. Most people knew that meant do the whole problem, including all parts. Even if you got, say, part A correct and then didn't get part B, then you still needed to do part A and part B on the redo. However, since this is the first time out, there were a handful of people who did only the part that they got wrong and not both parts or whatever. And so I let that go this time. But next time, remember, each problem that has an assigned number of points, like problem number 6 had 10 points. If you didn't get all 10 points, then you had to redo all of problem 6. Does that make sense, everyone? Another one instance I saw was someone put a little bit of misunderstanding and did a little more than they needed to. I gave the option that if you got everything correct on the whole test, you could still get the extra credit by turning in a sheet that said, I did everything correct the first time, and you're good. But you don't need to do that if you miss some problems and you have to do some rework. You don't need to write that down for each problem that you got correct. The problems you got completely correct, just leave off of your, you don't have to do them at all. One person also that I saw had done a couple of the required problems, and that was another requirement that you had to do all the problems you missed something on, and that would be. So I think that's it. again, it was curious to me that everyone who had missed problem 4 did all of the parts of problem 4, even if they got some of the parts right. They redid all of it. But then they would only do one part of, say, problem 6. So that to me is a little curious that we would change our plan of operation in midstream like that. But again, this one time I let that go. Now I will make one comment. Problem 4D, I don't think anybody got correct. I'll just talk about that briefly. So look at problem 4D. Question says, find all C values so that the limit of f of x as x approaches C is equal to 2. And most people were able to accurately tell me, right here, I guess, that on this picture, there's 2. Most people would say, yeah, they're at C equals 0, the limit seems to get close to 2, and I agree with that. And then to point out here, this is another graph than this. So a lot of people put it's very close to correct answers as C is equal to 0, but also C is an element of, and this is incorrect, I'll tell you the correct answer, 2 to infinity. That's almost correct. Because notice that, that for example, at 3, x equals 3, c equals 3, the limit is back 2. And at x equals 15, the limit is back 2. So this is almost correct. But why can we not include the 2, right there, the 2, why can we not include that 2? How did the weather people do it? I was just looking at the screen, trying to put my finger in the right spot, and I'm like, how do they do that?
They practice.
They practice a lot. Anyways, how is the 2 should not be included in this answer up here? Explain that. The correct answer is not a square bracket right here. The correct answer is parentheses on the 2, and why? Why can we not include the 2 in this answer? I get why a lot of people put 2 as included. Some people just said it was equal to 2, which is, again, I kind of get it, but why is it not correct? At x equals 2, you're like, well, yeah, the value is 2 at x equals 2. But is the limit at x equals 2, is the limit equal to 2? Well, let me read. If you don't know the answer to the question, look at part 4A. Same test, same problem, 4A. What are they asking?
What did they? Just looking at it.
Volunteer to read number 4A and tell us the answer. I mean, almost everyone got it right. So somebody got to be able to read it and tell me the answer.
I'll read it.
Yeah, thank you.
Okay. The limit of f of x as x approaches c does not exist, but f of c does exist. And the answer is 2.
So at c equals 2, the limit does not exist according to 4A, but f of c does exist. So again, turn back to 4D. We're looking for the limit x approaches c of f of x equals 2. Limit x approaches c of f of x equals 2. So at x equals 2, does this limit equal 2?
No.
Oh, because you just told me at 2 it does not exist, so it can't be equal to 2. Are we clear on that? The limit from the right and left don't match, so it's not equal to 2. So there, I see why you make mistake, but be careful, please. Okay. Any last quick questions? We need to move on. About the logistics of this?
The logistics?
The logistics of the rework, any questions on that? We'll make one more comment on 6A, problem 6A. A few people gave the incorrect delta because if you work it out, you do a delta left side and a delta right side, and they come out to two different numbers. And which one are you supposed to pick of those two different numbers? So several of us picked the bigger of the two. We're trying to get the biggest that works. Pick the biggest of the two numbers. If you pick the biggest of the two numbers, then you've created a delta region that's outside of one of the sides. And you're so far out here that the smaller one has some room that doesn't work. So you got to pick the smaller of the two so that you're inside of both of them. That's your maximum. So several people did that. They picked the bigger of the two, which is incorrect. The smaller of the two. Okay. I think those are the two big questions that I saw on the test. I still had trouble on the rework. Right. What about section 1.6? By the way, Rezo posted a question on the forum last night about section 1.5. I don't know which problem was it. Rezo, do you remember which problem you asked about?
45.
45?
Yes, 45.
The answer in the book is incorrect. The answer that Rezo got in his post is correct. So I apologize that the grad students who wrote the answers were incorrect. Now, on 1.6, you were asked to read it, and we're going to talk about it today some. Let's just examine the theorems real quick, and I don't think they're too exotic to understand, so let's make sure we're clear. So I'm just going to quickly scan over these theorems and see if you have questions, and then we'll get to problem 1 and talk about it some. So on page 139, from 1.29, you have a theorem that talks about a limit where the denominator approaches 0 from the right or the left. So it indicates that when you do approach 0 with a fixed numerator, a constant numerator, then your overall fraction approaches infinity, which hopefully makes sense to everyone. Does it make sense, that theorem? Did you go over that? Maybe an example. Everyone get that? Didn't we do one yesterday with we looked at the limit from the left side and limit from the right side. We had like a 0 plus and 0 minus. Didn't we look at that yesterday? Yeah, on the piecewise. Remember one of those pieces we had a limit from the left side went one direction on infinity and limit from the other side went a different direction or something like that. Well, that's what this theorem is talking about. So we've already experienced that. Let me just check what we'll put that. So, Kyle is not here again. Okay. So one more time, any questions on this theorem about if the denominator gets close to 0, you have to understand which side of 0 it's on. Why does it matter which side of 0 the denominator gets on to understand what the overall result is? Why does that matter? my question.
Isn't it because it tells you whether it's positive infinity or negative infinity?
Exactly. If you're approaching 0 from the left-hand side, then that means you're left of 0, which means you're a negative number. If you're dividing by a very small negative number into a positive numerator, then you get a negative infinity result. Vice versa, if you're approaching 0 from the right-hand side, then you're right of 0, so it means you're a positive number. If you're dividing into a positive numerator, you get a positive number. So knowing which side of 0 you're on is exactly right. Is important. It tells you whether you're going to infinity or negative. Good. The next theorem at the bottom of the page talks about instead of getting close to a fixed number and having an infinite output, now we're getting close to infinity as our x value, and we're finding out what happens with the function. And we're looking at the if the denominator grows to infinity or negative infinity, it doesn't really matter because the overall result becomes 0. You've got a constant numerator, then you divide by infinity, you're going to get close to 0 eventually. So that ought to make sense as well. Questions on that one? So if you're dividing by an infinity, even if you're dividing by negative infinity, because you get very large in the negative direction, if you're dividing into a positive number, you're going to have a negative answer, I grant you. But the answer is negative, but it's getting really close to 0, so you're going to have a limit of 0. Okay. The next page, theorem 1.31, has some important knowledge theorems that you should hang on to. That ought to be, again, obvious, I think, but let's just make sure. I'm going to write a couple of these down here just to emphasize it. So it says if k is greater than 0, let's go over there. If k is greater than 0, then limit x goes to infinity, x to the k equals infinity. That ought to make sense. You got an exponent k on a variable x, and if that k value is positive, then as my x values grow unboundingly, then the overall response will also grow unboundingly. But also, x to the negative k, if k is positive, then x to the negative k can be rewritten easily as a 1 over x to the k, and that answer turns out to be 0. It ought to make more sense why it's 0 now, because if this is growing to infinity, and here we're doing with a negative exponent, that's like putting an infinity in the denominator, and so the result is 1 over infinity, which gives me a 0 response. Same thing with an exponential. This is power. This is exponential. K is greater than 0, then you have, excuse me, and then x approaches infinity of e to the k x is equal to infinity. That works for any base, really, but in particular base e. So you're going to grow to infinity, any base bigger than 1, I should say. And then at x approaches infinity of e to the negative kx, it's going to be in a similar fashion. 1 over e to the kx goes to 0. So those are a couple of nice ones to remember, and very particular because you use those in a lot of situations. For C, kind of natural log, a of x as x goes to infinity is also infinity. You ought to be able to think about all these graphically as well, since we're talking about going to infinity. This is essentially just talking about end behavior. So you've heard that terminology in pre-calculus, end behavior, right? What can you tell me about end behavior of a power function? Like if this is x squared, that was x squared. What can you tell me about the end behavior of that? X goes x squared, it's like that. Both ends are up, or both, you all learn that pre-calculus, right? Both ends up, both ends down, down, down. Well, what does this say? The right end of x squared is infinity. It's up. Okay. Seems like that's obvious to me. If it was cubed, then its right end of x must be up. Same thing with e to the kx. What does e to the kx, what does the function, exponential function look like? Now remembering what that looks like. Kx. Anybody? Y equals e to the kx. Exponential curve, what does that look like? Yeah, it's got a horizontal asymptote on the back end, and it gets really steep on the right end. That's exactly right. So this is saying. Okay. Then the other one was logarithm. It says x goes to infinity of logarithm of x, you get infinity. So what's the logarithm graph look like? Remember that? Brendan, do you know what the logarithm graph looks like? It'd be helpful if we just knew these things, folks. You don't have to get a perfect picture, just you have some inkling what it looks like.
It's got a vertical asymptote on the y-axis.
Yes, vertical asymptote on the y-axis. That is exactly right. And then it crosses the x-axis and continues to grow in the positive direction. That's what the next theorem said. Next part of the theorem says. Exactly right. Next, the fourth part has sine, cosine, all the trig functions. They all have periodic behavior. So as x goes out to the end of infinity, you don't get a limit. It's a periodic. However, inverse tangent is a really unique one that's really cool, and we see it again later in count 2. It's cool because it is bounded. I'm going to go right here. So hopefully you remember this from your pre-calculus days. That I'm graphing y equals inverse tangent of x. It is a mirror image across the line y equals x. Inverse functions are always a mirror image across the line y equals x of tangent of x. Except for we only chose one cycle of tangent so that this becomes a function instead of a non-function. And this is negative 1/2 pi. This is positive 1/2 pi. So inverse tangent is bounded by 1/2 pi. And so it's a nice function for modeling a lot of situations that we'll see later. But because of that, then we can talk about the limit. So as x goes to infinity, tangent of x gets, inverse tangent of x gets close to 1/2 pi, and as x goes to negative infinity, inverse tangent gets close to negative 1/2. Okay. Then we have indeterminate forms on page 141. And we've already discussed that a little bit, but not a whole lot. We'll just more. There lists several indeterminate forms there that you need to be familiar with. On page 141. We've seen 0 divided by 0 as indeterminate. Also infinity over infinity. May or may not turn out to be 1. It could be almost anything. 0 times infinity. We've always heard since third grade that 0 times anything is 0, but that's any times anything that's not infinite, any fixed number. So 0 times infinity, when we're talking limits, may not be 0. Infinity minus infinity may not be 0. It all depends, folks, on how fast one part is growing versus the other. So if for example, 0 times infinity, if the factor that's going to 0 is getting there faster than the factor that's getting to infinity, then the result will turn out to be likely 0. It matters. That's what we're looking into. Other forms that are indeterminate, 0 raised to the 0 power. We've always heard again, anything to the 0 power is 1. Well, that's true as long as the base is not 0. And or infinity. So either 0 or infinity to the 0 power is indeterminate. And 1 to the infinity is also indeterminate. We've always heard that 1 to any power is 1, but that's not true if that power is not a fixed number. Okay, so anything else that you see is going to be non-indeterminate. And on the next page, they actually list some other forms that sometimes students confuse as indeterminate when in fact they are actually determinate. So look across on part A. On part A, all of the examples they give you have a result of 0. And hopefully it makes sense to you. 1 divided by an infinite large number is effectively 0. 0 divided by an infinite large number is 0. 0 divided by a fixed number is 0. 0 to infinity is 0, and 0 to the 1 is 0. So all these are things that could almost look like they're indeterminate, but they actually all turn out to be 0 as an answer. And then the bottom row, part B, have infinite limits. And so, again, that makes sense. If you have 1 divided by close to 0 from the right, it goes to infinity, and so on across there. If you add 2 infinities together, you're going to get infinity. If you multiply 2 infinities together, you're going to get infinity. Infinity raised to the infinity, that sounds like, what's the name in the Toy Story or something? Is that the name?
Yeah.
And infinity to the 1 power is also. So we have some things that are indeterminate and some things that are not. The answer is as clear as it should be. Then we have 2 special trigonometric limits that we'll need later in life as we go on into further calculus study. So we need to take a look at those real quick. Question. I'm sorry, question. I'll look at that. Go ahead, question.
I had a question.
Yes.
I had a question about the indeterminate forms for limits.
Okay.
We've had to work with 0 over 0 before, but I don't understand how you'd practically get most of the other ones. Like how
Well,
you
that's what we have to work on. Is most of those require some kind of algebraic manipulation and involving factoring or rewriting, so that you get it into a form that you can do something with. So it's not always easy. It just, but it will involve some algebraic manipulation. Now, it won't be the manipulation may not be identical with done before, where we simply factored out an x minus 3 on top and bottom and canceled. Maybe that's simple when it's already infinity over infinity, but if it's 0 times infinity, then we may have to try something a little different. Okay. So we'll try to do some examples there. Okay?
Fine.
Questions? Let's do one real quick. Here's an example. We'll work right here.
that 3/5?
Okay, so I have written up a function on the board, a rational function, so it's got a polynomial numerator and a polynomial denominator. And in pre-calculus, in fact, in the pre-calculus review, we saw a statement that said if the degree of the numerator is equal to the degree of the denominator, then the ratio of the coefficients will give me my horizontal asymptote. You recall this statement that we studied in pre-calculus?
Mm-hmm.
Everyone remember that statement?
Mm-hmm.
The coefficients here are 3 and 5, so that gives me a horizontal asymptote of 3 and 5. Okay, great. You were told that in pre-calculus, and you said amen. Now we're going to show that it's in fact true by using limits. Okay? So a horizontal asymptote involves what goes on at the ends of the graph. Okay? Horizontal happens at the end. So means we need to take limit as x goes to infinity. So we're going to take the limit x goes to infinity of the function. So this is 3x to the 4th minus 6x squared plus 7 over 5x to the 4th plus x cubed minus 9x. We're with me to there. I haven't finished the problem. I haven't shown anything. All I've done is written down what I need to do. But do we understand why this is what I need to do? By looking at the limit as x goes to infinity, we're looking at the end behavior of this function. And the end behavior should be that it gets close to, the answer should be, this limit should be an answer of 3/5. So we clear that's what we want to achieve. If the answer of this limit is 3/5, then we've shown that as x goes out to infinity, this function gets close to the number 3/5. That means it has an asymptote at 3/5. Is that clear now?
Yes.
All you gotta do is find that limit. I know it's going to be 3/5 because I planned it that way, but how do I show that? Well, one thing I might try is the continuity theorems we've seen.
Oh yeah,
So,
those things.
plug in. Well, I can't really plug in infinity, but you can imagine plugging it in. So what happens if I plug in infinity here? Let's see. So infinity to the 4th, that's like really, really, really big. And infinity to the squared is pretty big, but not quite as big. So when I subtract it away, I still got a really, really, really big number. And that's a 7. So basically, this comes out to be. I missed that. What was that?
It just sounded nice. Keep on going.
That's just a 7. Who cares about 7, right? I mean, in the grand scheme. Is that? I don't know.
Okay.
What about the bottom here? So you got an infinity to the 4th power, which is really, really, really big. Then you're going to add an infinity cube. Now we really, really are getting somewhere. You're going to subtract off 1 infinity. Okay, well, I'm still really big, so that's an infinity. So now, that's indeterminate form, right? So this is indeterminate form. In fact,
Oh no.
what I'm going to do is I'm going to factor. I'm going to factor.
Okay.
I'm going to factor. Now, when I say factor, everyone's mind immediately goes to x minus 3 times x plus 2. That's fine, but that's not what I'm going to factor. I'm going to choose on this one, because I feel like it, I'm going to factor an x to the 4th out of everything. So I'm going to have an x to the 4th times 3 minus 6, 6 over x squared plus 7 over x to the 4th. And I'm going to factor an x to the 4th out of the denominator as well. That's going to be 5 plus 1 over x minus 9 over x to the 3rd. Agree that that's an equivalent statement of what I had before in terms of factoring? In other words, if you unfactor it, i.e. if you distribute it, you get back to where we started at.
Yeah.
Now what?
Well, you want to do a
Well,
cancel?
as long as x is not 0, which is not going to get anywhere close to 0, then I can cancel the x to the 4ths. So this is equal to limit x goes to infinity of 3 minus 6 over x squared plus 7 over x and 4 over 5 plus 1 over x minus 9 over x cubed. And just as a note, x not equal to 0. And it's not going to be, because I'm looking way out at the ends of the graph. I'm not worried about what happens at 0. Now try your theorems. So let's see. If I apply the quotient rule, remember the quotient rule where you can do the top and bottom separately? That's what I was doing a moment ago. And I can do each term by term separately. I mean, just remind you, you've got a quotient rule, you've got a sum rule. That's what I was doing a moment ago in my head. Well, I'm going to do it again. So limit x goes to infinity of the number 3. Well, you're just hitting 3, 3, 3, 3 for as long as you can, so you get tired of it, just write down 3. Okay, so what happens when x goes to infinity for 6 over x squared? Yeah, by theorem A over here, 1 over x to the k goes to 0 as x goes to infinity, the top row right over there. So I've got a 6 times 1 over x to the k, so that just makes it 6 times 0, which is just, what about 7 over x to the 4th as x goes to infinity? 7 divided by a really, really, really big infinity is 0. This makes a 5. This makes 1 divided by infinity is again 0. And 9 divided by infinity is again 0. So how about that? 3/5. So what they told you in pre-calculus was not a lie after all. There's actually some rational reasons that that rational function has a 3/5 horizontal axis. And we've handled an infinity over infinity one way. Okay. Okay, so that covered some ground. That covered end behavior, like you learned in pre-calculus, handling infinity over infinity. Good. Now we want to look at other two limits. We'll actually try to prove the first one, and we'll just say the second one is obvious. Follows from it. The rule. The book does the proof. It's a nice proof. Simple proof. Okay, so limit of sine theta of theta as theta goes to 0 is 1. So we've seen that before. We did an example with that with a graph earlier on, maybe even with a table. Now we want to do it more formally. So sine of theta over theta, if you graph that, if you recall, the graph had a hole in it at 0 because you can't divide by. This is theta, this is y. And then it was a sine wave that got damped out. Got damped out because you're dividing by, you're taking that sine wave and you're dividing by this theta that's getting big so that it damps out your sine wave. That was the graph of it. And we saw as x gets close to 0, theta gets close to 0, the y value gets close to 1. So we want to show that limit the theta goes to 0 of sine of theta over theta equals 1. And the easy way to do it is with the squeeze theorem again that we saw before. So once again, this will be part of a unit circle. So this is 1, this is 1. If this is my angle theta right there, that means this dimension right here, in equivalent units is the 1. That's theta in the same type of measurement system as that 1 is in. We also know that if I drop a vertical line right down here, this dimension is sine of theta. We know from pre-calculus trig, if you take opposite over adjacent on a right triangle, you get tangent. But what you may not recognize, and I hope the purpose is up. And tangent is also named not because of that, but because if I draw
Oh my gosh.
I draw that, this triangle that involves the ratio of long side out here to 1, so opposite over adjacent of the bigger triangle, that ratio is the same as opposite over adjacent of the small inside triangle, but we all agree with that, just by similar triangles. Therefore, this long side out here is actually called tangent of theta. So from that picture, it's easy to see the squeeze theorem coming up. So we've got, let's see. Looks to me like sine of theta is smaller than theta. Is that right? That is smaller than tangent of theta. What? I'm missing something.
I don't think I get it.
What am I missing? Sine of theta. Well, that's right. I'm doing it right. What am I missing? Okay. Well, in other words, I'm not here. You don't understand? I've got this. That looks good. I see that this side is smaller than that arc, and that's smaller than that side there. That makes sense to me. But I don't have it tied to this. So how can I make this somehow relate to that? Are we following my question? I'm like, that makes sense to me. I see dimensions geometry that makes sense, but that doesn't really tie directly to this. Suggestions?
Would you divide theta from the whole inequality?
Well, that's a good idea. What I think I'm going to do, though, is I'm going to divide by sine of theta. It's a good suggestion. I think we could do it your way, but I think if you do it this way, divide everything by sine of theta. Then we get 1 is less than or equal to theta over sine of theta. So that's right. So now what happens if I divide tangent by sine? What happens? Yeah, you just get 1 over cosine, because the sine of theta is canceled. That's exactly right. Now I'm getting close. Notice that this function here is kind of similar to that function, and it's squeezed between 2 outer functions. So all I have to do is get the reciprocal of it. Well, the great thing about math and numbers is if you take the reciprocal, what happens with the inequality when you take the reciprocal of these numbers? Switches direction. Like, you know that 2 is less than 3, but when you take 1/2 and 1/3, that ordering switches, right? So I switch from less than to greater than.
It's crazy.
That's crazy, isn't it? How numbers are like that. And now we're there. So if we do on this one like we did yesterday, the limit theta goes to 0 of 1, and that's just 1. And if we do this one, limit theta goes to 0 of cosine of theta. That's 1 also. So we have the limit of theta goes to 0 of sine of theta over theta is between, is no bigger than 1 on the left and no bigger than 1 on the right. So it's between 1 and 1, so it must be 1. Okay, so okay, and then the other one is right there. It says limit theta approaches 0 of 1 minus cosine of theta over theta is 0. And I would point out we're both indeterminate, but we have a defined value. So right here, we just proved this statement. So notice, if you quote plug 0 into this function, what happens? If I plug 0 into sine of theta, what's sine of 0? 0. And I got a 0 on the bottom. So this is really indeterminate, but the theorem is telling me it's indeterminate 0 over 0. So it's 0 over 0 indeterminate. But the theorem is stating, okay, it's indeterminate, but from now on, we know that indeterminate simplifies to a 1. You don't have to cancel or anything. It just is going to be 1. But now try the other one. It says limit theta goes to 0 of what? Cosine of theta minus 1 over theta. Is that what it says?
No, it's flipped.
1 minus cosine. It'll work either way, but we'll write it the way the book does it. Okay, that one turns out to have an answer of what? Well, it's 0 this time. But now notice, that's what the theorem says. But now notice once again, if I just try to plug in, what happens? Plug in 0, you get 1. Cosine of 0 is 1. 1 minus 1 is 0. So you still get 0 over 0 indeterminate. But this time that indeterminate comes out to be 0 instead of 1. So once again, indeterminate, the reason it's called indeterminate is because you can't, it's not obvious at first glance what the answer is. You can figure it out. This time we proved this not by doing factoring and canceling, we proved it with some geometry. And they show the graph of the cosine, this function here. They show it on page 143. At the bottom right, that second function, 1 minus cosine over x. It is again on the ends. It's a damped cosine wave, but then it comes right through the origin and has an open circle there. So it's a little different graph. Okay, I think that covers all the material in there. So now we want to take a minute and talk about problem 1, and then maybe try some more practice. So you're asked to read and try problem 1. Now that may mean you had some trouble because we had talked about it. Now we can talk more. Problem 1 gives good conceptual questions to discuss. Even if you get it wrong, it's okay. We learn from our mistakes. Let's see if we can do this. So 1A, volunteer to take 1A. Justin said he'll take it. Thank you.
Here.
So that's true. That's one of the theorems in the book, essentially. You're right. They got some very specific ideas, but they also kind of talked in general about that. Right. Good. 1B, volunteer. Elise, could you take it, please? Or somebody, Mason raised his hand, either one. Mason, go ahead. You raise your hand.
True or false? If f of x as x approaches infinity from the right, then 1 over f of x approaches 0 from the right. And I said this was true. This is theorem 1.38.
Yes, yes. Okay, good. So we've got this. 1C. Enzo, you got your hand up?
I had a question, actually.
Okay.
How do you approach infinity from the right?
Yeah, I think that's a good question. I want to be like, I don't know. So I'm going to say that might be a typo in the book. So let's just say it's infinity rather than infinity from the right. That's a good question. Think about that, folks. How do I get approaching infinity, which is out here, on the right-hand side? It's an excellent question. I'm going to say I don't think that's what they intended.
Okay.
Good question. What else is? You want to take that one? Take, so you'll take the next.
True or false? Limit initially has an indeterminate form. It never solved. That's it, false.
False, because we just did some here. This was a theorem, and we proved it with some geometry. Here's one that was indeterminate. We still figured it out. So that one's absolutely false. Although you might run into a few occasionally that you can't figure out very easily. But most of them we'll see are in some kind of fashion like we can do. Okay, good. 1D. There's not. Let's get somebody else. Rezo, thank you.
Okay, true or false, a limit does not exist if there is no real number that it approaches. And I said that is true. I mean,
That is in fact true.
It seems kind of self-explanatory, honestly.
I mean, the only time that we almost think of it as existing when it's not a real number is if you're coming to an vertical asymptote and both sides go to the same direction, then we can say that the limit as x approaches c is infinity. But that's still not existing because it's not a real number. So I agree, it's self-explanatory. What about E? Oh, could you take E, please?
Sure. True or false? As limit forms infinity squared approaches infinity, and I got that was true because infinity is not a real value. It's like not a defined value, so if you square it, it's kind of like just approaching itself because it is so big.
That's correct. And one of the theorems mentioned infinity times infinity being an infinite value. So I think that infinity squared is just infinity times infinity. What else? Eddie? I agree with that. That's true. That one kind of relates to the part B over here on this board. Base E to the KX. KX goes infinity. That's going to be infinity. And so it'd be an easy thing to change E to 2 and make that 2 to the infinity. So I agree. That's related to that theorem. How about G? Sydney, could you take G, please?
True or false? As limit forms infinity minus infinity approaches 0. And theorem I said it was false, and theorem 1.33 says it's indeterminate.
Correct. If it's indeterminate, it might actually turn out to be 0, but we don't know that until we do a little bit more work. That's exactly right. H. Boom, could you take H, please?
Who's boom? Did he say boom? What did he say?
Boom?
Boom?
Sorry. I think that was false. Oh, sorry. The limit of a function f as x approaches c is always equal to the value of ft, provided that f of c exists.
Dang.
That is false, I agree. Clear examples from the test when you had that jump discontinuity. F of c existed, but the limit did not. Okay, good. Question. All right, so give it back. One, two, 13. Part 1B.
B.
D. What we said is true. Yes, that's one reason.
What about if you did like limited the I X over X? Would you do it if do everything except Y? Is that not true?
Limit does not exist if there's no real number that it approaches. So that example you gave is it does exist. Why is it a lie? It does exist. You're not providing a counterexample to the truth concept. Okay. It said if the limit does not exist, it says limit doesn't exist if there's no real number that it approaches. So if there's no real number that, so we write it in the if there's no real number that it approaches, then the limit does not exist. So the only way you can contravene that is to give me an example where the limit, if the limit does not exist, give me an example where the limit does not exist, but there is a real number that it goes to. That's not possible. Okay. Any questions on that? Anybody? Did you hear that question from Justin and the response?
No.
Not really? Okay. He was asking about 1D that Rezo asked or answered. And the question says, a limit does not exist if there is no real number that it approaches. And he suggested an example where you can calculate a limit. He said, well, pi x over x. The x's can cancel if I'm like going out to infinity or going to whatever. The x's can cancel and I get this limit of pi. And I agree with that. But the problem was that does not contradict the statement. The statement is, if you rewrite it with hypothesis first and conclusion second, you would say, if there is no real number that it approaches, then the limit does not exist. So you have to give me something that does not, if there's no, that does not have a real number of approaches. So you got to show me something that does not have a real number that it approaches. But then to contravene it, you got to show me that the limit does exist. So something that doesn't have a real number that it gets close to, but then say that the limit does exist. That's not possible. So he was trying to come up with a counterexample, but the approach was coming at it from the backwards direction. Remember, if then, to show that an if then is false, to show an if then is false one more time, you have to assume the if is correct, and then show me that the then doesn't necessarily follow. Give me something that doesn't work out on the then part.
That's true.
Okay.
Oh yeah, actually, that makes me curious about something.
Yeah, Reza?
Does an infinite limit not exist?
If the limit of x approaches c of f of x is equal to infinity, is that what you're talking about?
Yes.
So yes. So limit x approaches c of f of x equals infinity.
Mm-hmm.
We can write this, we can use this writing, which is not, it's allowed. This is saying that as I approach c from the right and from the left, the output is getting close to infinity. And since both sides are going to the same infinity, the plus infinity, then we can write a plus infinity there or a negative. So it's either both sides going up or both sides going down, allows us to write that. But technically, this is considered does not exist. So, all of the cases of does not exist, this is the one time when we allow you to write a symbol to represent an answer. That symbol happens to be infinity. Does that make sense now? Any other time that it does not exist, if it oscillates, if you have a jump discontinuity, all those other cases you have to say does not exist. If you write does not exist here, technically that's correct. We just allow, in this special case, to use infinity as the answer, even though really it does not exist. Everyone follow that question and answer? It's one special case we allow. Okay, let's do one quick homework problem so you can practice on your homework.
Yes.
Okay, how about let's do problem, here's a simple one, 68. So it's not an actual homework problem, it's one that you're similar to it. I'm going to leave that up there because I'm going to need that. What does 68 say?
68. Oh.
What does it say?
It's on 3x.
Okay. How do I handle this problem? Well, to me, it looks a lot like this statement, but not identical. So this statement and this statement look pretty close. But I need to manipulate it so that I can now use this theorem. So the first thing I'm going to do is apply my multiple rule. I can factor out a 1/5. That was my multiple rule. But I still have some concern because up here, the input to sign in the theorem is the same as the variable of my limit. Here, the variable of my limit is x, the input to sign is 3x. They need to match precisely. So here's what I'm going to do, a little game of algebra again. I'm going to choose multiply by the number 1, but the number 1 I'm going to choose to multiply by is over 3. So I've just rewritten my expression using 3 over 3, because 3 over 3 is the number 1, so I haven't changed anything. Now I'm going to factor this numerator 3 out of the answer. Excuse me, not that, out of the function, pardon. And that is going to be sine of 3x over 3x. Now it's by the multiple rule. Almost there. Now we're going to do a substitution. I'm going to pull up here where I have more room, right? So, I'm going to write down what my rule is. Substitution.
Oh, gosh.
I'm going to let 3x equal, I'm going to use W.
I can't even read.
As x goes to 0 and W goes to 0.
Can you zoom in a little?
Over on the right here.
Yes. Or just the board in general.
Come on. There we go. You see that now?
Does that say let 3x equal w?
Yes. Let 3x equal w, and then as x approaches 0, then w will approach 0. This is going to let me to write I'm substituting a W in place of the 3x business so that now this looks exactly like the theorem. And I have 3/5 times 1 by this theorem. 3/5.
Dang. That's smart.
Okay. What about time now? Got one more minute. Other games you can play, like on problem, I don't know. Like on problem 56, I would suggest on 56 that you play on 56. If you look at that real quick, I'm not going to do it for you. We won't run out of time. But if you look at 56, in my mind, it looks very similar to this problem. They're not asking you to show that there's an asymptote, but you're doing limit approaches infinity of a rational function. And I would suggest that you choose to factor x to a power. My question is, what should you choose to factor? Now, this time up here, I chose x to the 4. What made me choose x to the 4 as my factor?
It was the biggest one.
Exponent that I see. In the in there. So if you factor that, I think that will be helpful. Okay. Don't forget that you can factor exponentials as well, like in number 58. 58 involves exponentials. You can do some work with that as well. So quickly. So 2 to the x is equal to e to the x times 2/3 to the x. Do you all agree with that? Two to the x equals 3 to the x times 2/3 to the x. Do you all agree with that? Never mind when you look at number like something like that.
I'll take it.
Okay. Well, I guess we're out of time, so we'll see you tomorrow. That's section 6. We have a test. 1.5 and 1.6.
Brittany, are you going to the computer lab? Okay.
One to the power of 8 or infinity?
I like read it last night.
Well, that's kind of a loaded question. I mean, I guess the reason would be because infinity is more of
So
an
we're gonna be
idea
like,
than
is
a
this a
number.
chemical?
So it's just because it doesn't
I
exist.
bet I'll forget something like alkaline metal.
Well, I mean, it exists, but it's more of a concept than a value.
I'm really close together, dude.
I mean, it's more of a,
Well, it's kind of like, I look at it as a program, I guess.
You're looking like
And
a Floridian
if something
guy.
doesn't exist, the computer can't compute
How much did you
it.
spend?
Right, so there's no answer.
well, the computer definitely can't compute infinity.
That's for this hour.
Yes. So I was sick yesterday.
He left me a note. I emailed you, dude.
You know me? Where'd you
Oh
go?
dang!